Wah. Mm, mm. Today's another day.
What do your phone screen, your basement, and the road outside your house have in common? They are all made of sand. Glass, meters thick. To build a typical home in the United States, beaches and protected marine sites are eroding at a rapid pace. The amount of concrete used worldwide is not tracked, but the amount of cement is. In just 3 years, from 2011 to 2013, China used more cement than the US did in an entire century. In order to make concrete, you need roughly 1 part cement to 7 parts aggregate or more, depending on the recipe, meaning China's demand for sand is truly enormous. Or more. In order to make concrete, you need roughly 1 part cement to 7 parts aggregate or more, depending on the recipe, meaning China's demand for sand is truly enormous, and the rest of the world needs even more. In some places, sand is also used to expand a nation's geographic footprint, and it's not just for construction projects. We also use sand to restore natural landscapes and ecosystems. Globally, most beaches and protected marine sites are eroding because of climate change and other human impacts. To combat this, engineers in some places will dredge sand up from the ocean and dump it back on beaches. The most populated beaches in the US require sand to be brought in regularly to keep them from eroding away completely. Half of the coastline in the US is eroding, to the point that we've had to fill beaches with over 1.3 billion cubic yards of sand. The cost of all this sand, over $10 billion. And beach sand doesn't stay where you put it. It's consistently being washed out to sea. So beach restoration is always going to be an ongoing process. Here's the real problem, though. Whether it's ecosystem restoration or manufacturing, that sand has to come from somewhere. And the type of sand can really matter because, yes, as discussed, there are types of sand. The round grains produced by wind weathering, the kind that make up desert sand, aren't really suitable for construction because they don't bond properly when making concrete. The water-worn sediment on coastlines and in riverbeds is rougher and more angular, and the jagged edges connect together like puzzle pieces to create a strong binding perfect for concrete and asphalt. But because we need so much asphalt and concrete, water-weathered sand is in big demand. In particular, sand mined from riverbeds is the most desirable. That's because sand from beaches
Wow, we got another one?
or the ocean floor contains contaminants, notably salt, which has to be washed out before the sand can be used. Our enormous hunger for just the right kind of sand has caused some serious environmental issues. Removing sand from river systems causes their banks to erode and increases the risk of floods. All of this is harmful to aquatic species and humans who often rely on river-fed aquifers for drinking water. Sand mining can also change the pH balance of water and pollute river basins, further jeopardizing these fragile ecosystems. In many countries, riverbed mining has been largely phased out because it is so destructive, but it's still practiced in some parts of the world. Unregulated riverbed sand mining is leading to the destruction of Vietnam's Mekong Delta, an agriculturally important area of Southeast Asia that's home to 20 million people. The delta depends on sediment from upriver to maintain its landscape, particularly as the sea level rises. But sand extraction is removing the sediment before it can make its way to the delta. As countries limit inland sand mining, there's been greater demand on marine and coastal sand, but that's more expensive thanks to the need for salt removal. Dredging marine sand also kills marine organisms, of course. It destroys coral reefs and affects water circulation. Even when engineers are just restoring beaches, pulling sand up from the ocean floor is harmful to the flora and fauna that depend on that landscape. Marine sand is also crucial for protecting coastlines and islands from severe weather, like the destructive storm surges that accompany tropical storms, destroying coastlines and causing inland flooding. Removing it or mining it makes coastal lands more vulnerable to storms and sea level rise. Sand doesn't have to come from water. It can be mined in inland quarries, but they require open pit mines, which are a real not in my backyard kind of problem. Who wants to live near a giant hole in the ground? Since sand mining is so destructive, some governments have imposed bans, but the need for sand, of course, persists, so it gets shipped from all over the world. Sand shortages have even led to violence and crime in some parts of the world. India and Morocco have sand mafias, I'm not making this up, that export illegally mined sand, and in Italy, sand supplies are heavily influenced by organized crime. This is real. This stuff is expensive. It is a mob business. Even when it's legal, sand is pretty heavy, and it often needs to be transported by cargo ships, giving sand a serious carbon footprint. In Dubai, for example, to build the world's tallest building, the Burj Khalifa, they had to import sand from Australia. And yeah, Dubai is in the middle of the desert, but they couldn't use that sand to make structurally sound concrete, so it had to come all the way from down under. Right now, you are probably thinking, can't we just make sand? Well, we can. But it is made from rock, which is still a finite resource and still has to be mined from a quarry. Manufactured sand is created by running rock through a crushing machine, and that stuff is actually even rougher than river sand. The angular grains bond together so well that it's actually better for making asphalt. However, studies suggest that manufactured sand requires more water to bind it together compared to water-tumbled sand. It also doesn't look as nice. So even though it can work, construction companies prefer river or coastal sand. Luckily, we have some other options in addition to manufacturing sand. Some researchers have proposed harvesting sand from Greenland's retreating glaciers. Now, no one wants to melt the glaciers, but due to climate change, Greenland's ice sheet is already shrinking at an alarming rate. And glaciers are filled with sand. So as the ice melts, it unearths and dumps a lot of potentially usable sand into the sea. This is sand that was shaped by water, so it has the potential to be suitable for construction. In a paper from 2019, scientists suggest that Greenland could become a large exporter of sand if it collected the sediment from melting glaciers. Now, it's worth noting that this is purely speculative at the moment. It is not happening yet. And since Greenland is very far north, the sand mined from the ice sheet would probably need to be shipped great distances, which would be expensive and have a substantial carbon footprint. Scientists are also investigating alternatives to rock and natural sand that could be used in concrete. These concrete alternatives include replacing sand with iron slag or fly ash, byproducts of the iron and coal industries that usually go to waste. Other suggestions have included using microplastics and shredded rubber instead of sand. Studies have shown that iron slag in particular makes a suitable replacement for natural sand. However, iron and coal production is dwindling in the US, meaning their waste is actually in short supply. Recycled building materials are also being examined as a possible replacement for natural aggregate and concrete creation, like crushed concrete, appropriately enough. Germany actually already recycles nearly 90% of the aggregate it uses. And yes, some have even tried revisiting that useless desert sand, though they haven't met with widespread success yet. Lastly, one California-based company has proposed that instead of using sand and concrete, it could be an opportunity to capture carbon. Their process uses carbon dioxide from the exhaust stack of a power plant to create synthetic limestone, which then can act as a substitute for the aggregate in concrete. They've already used some of this fancy concrete at San Francisco International Airport. So, there are options now, and hopefully there will be more in the future. The problem is that the building industry is very slow to change, and a major hurdle for these technologies is less science and more getting stakeholders to buy in. Natural sand, particularly water-worn sand, is a proven and effective ingredient in concrete. Builders know it won't make structures collapse. And when you're in the building industry, your #1 priority is that your building stays up. The demand will continue to be high until alternatives to natural sand gain more traction. So the next time you're at the beach, have a little appreciation for the stuff that's sticking to all your parts, because it's taken thousands, maybe even millions of years to form. And our world would not be the same without it. Thanks for watching this episode of SciShow, which was brought to you with the help of our patrons. There isn't a way we could finance content about sand mafias without our patrons. And also, patrons get access to cool perks like monthly bloopers and our community Discord. And also, they're just great. If you'd like to help us make videos like this one, go to patreon.com/scishow, because we do, as always, need your support. This episode is sponsored by Awesome Socks Club, a sock subscription for charity. Click the link in the description and sign up between now and December 11th to get a fun pair of socks every month in 2021. The color blue is kind of special. It has a reputation among biologists for being rare in nature. Except you've got birds, insects, flowers, sea creatures, even the eyes of some humans. Blue is everywhere. So, what's the deal? Well, it is actually pretty hard for living things to make blue pigments at least. Many of the natural blues you see are really made using structural color, microscopic structures that interfere with light to reflect color back to our eyes. But blue pigments are a whole different game. To make those, life has to jump through some surprisingly big hoops. Pigments are molecules that selectively absorb and reflect visible light, and they get their color from molecular structure and how the atoms are bonded to one another. So to understand why natural blue pigments are so tricky, we need to talk both biology and physics. A lot of the problem with making blue pigment comes down to how molecules can have colors in the first place. Surprisingly complicated. The very basic idea is that a molecule gets its color by reflecting and absorbing different kinds of light. If it mostly reflects red, it's red. If it reflects everything, it's white. If it absorbs everything, it's black. But to understand the problem with natural blue, you need to go a little deeper than that. So, imagine some generic molecule, one with multiple atoms sharing some of their electrons in the form of chemical bonds. Those electrons usually exist in what's called a ground state, with a set amount of energy, and it tends to be as little as they can get away with. But if you add some energy, like if an electron absorbs a photon of light, the electrons can jump to a higher so-called excited state. That's pretty straightforward so far. But one of the weird yet fundamental rules in physics is that electrons can only absorb light if it has exactly the right amount to actually get them to a new energy state. If it's too much or too little, the photon just bounces off the molecule. It has to be just right. And this is the reason why different things are different colors. Molecules have all kinds of different energy levels, and photons of different colors of light have different amounts of energy. Shorter, bluer wavelengths have the most energy, while the longer, redder wavelengths are like more laid back. They're just chilling. Less energy. Low energy red, or redder, different amounts of energy. Shorter, bluer wavelengths have the most energy, while the longer, redder wavelengths are like more laid back. They're just chilling. Less energy. Low energy red. So the shape of the molecule really matters because different structures within the molecule create those different energy levels. If its electrons can only jump to an excited state with high energy light, it's going to absorb blues. And the opposite is true as well. If it needs to absorb low energy light, it will absorb reds. And it turns out it is easier for life to make molecules that absorb blue and reflect red than the other way around. Blue rocks and minerals can hit that sweet spot thanks to either very complex crystal structures or the involvement of metals like copper and cobalt. This works fine for us humans when we're making things like paints, but metals like cobalt can wreak havoc in living things at high enough concentrations. So they're not necessarily something you want to like pack into your living cells so that you can have a nice bright blue color. Instead, life is generally working with carbon as a starting material. So to make an organic or carbon-based blue, we need something that a living thing could both make and keep around without poisoning itself. And it turns out the kinds of carbon-based structures that lead to blue are often really complex. But you can do it. Carbon's specialty is joining up in long chains or rings, and certain arrangements allow electrons to move throughout the chain. This arrangement is known as a bond conjugation. As the number of conjugated bonds gets higher, the amount of energy between the molecule's energy states decreases. That means it takes less energy to boost the electrons into the excited state, so the molecule will absorb lower energy red photons and reflect blue ones. So the more conjugation you have, the bluer the molecule appears. Problem is, the molecules that can accomplish this can be pretty tricky to use. Part of that may be that they're big and weirdly shaped, but the relatively shorter gap between the electron states can also make it easier for these molecules to react with other molecules floating around, which ruins all your lovely conjugation and destroys the pigment. So blue pigments are hard, but they are not impossible. If you want to find one, you can ask your liver about it. After all, there is one group of, if not super blue, at least bluish molecules that animals, including us humans, make and use on the regular. They're called biliverdins, and they're bluish-green bile pigments. Bile pigments are a group of compounds that come in several types and are all made from the breakdown of certain other compounds, often in the liver or spleen. And bile pigments come in all sorts of colors, including reds, yellows, and yes, blues. Now, biliverdins, the blue ones, never reach a real vibrant royal blue, but they do give organisms some color. Like they're good enough to color birds' eggs, butterfly wings, and some corals. But they're not normally used for their colorful properties, and doing so might actually come at a cost. Scientists haven't really examined the connections here all that much, at least when it comes to coloration, but we do know, at least in terms of health, you might want to be careful when you're tweaking the bile pigment production pathway. See, biliverdin is often thought of as a waste product, like other bile pigments, but turns out it appears to also function as an antioxidant. That's a molecule that can block other reactive molecules from damaging DNA or other parts of the cell. And biliverdin itself is usually turned into a yellow pigment called bilirubin, which is an even more powerful antioxidant, one that may have a role in protecting the cardiovascular system. There's some evidence to show that giving up biliverdin to color your body or shells could come at a cost to overall health. Researchers studying birds that make blue eggs have suggested that mothers with bluer eggshells make them by depleting their own biliverdin supplies, giving up those valuable antioxidants. Now, theoretically, an animal that uses biliverdin for coloration could just, make extra. But that would mean having extra bilirubin down the line, and bilirubin can be toxic in large doses. And then to get around that, you could theoretically tamp down on the activity of the enzyme that changes biliverdin to bilirubin, but it turns out that that enzyme also helps control a lot of other important functions in cells. So this part is a bit speculative, but there might be some evolutionary pressure to just not mess around here. So while some organisms do use biliverdin for its color, like those butterflies and corals, it doesn't seem like evolution has opted for it all that often. Again, though, we need more research to say that for sure, and also know for sure why this is or isn't happening. Now, this isn't the only pathway that can lead us to a blue pigment, and for this next part, we need to turn to our friends, the plants. Plants can make a type of pigment called anthocyanins. These are pigments found in blue flowers, and they have enough conjugated bonds to do the job. But they are, unsurprisingly, also super unstable. In order to work, they need very specific working environments, ones that might be harmful for the cells as a whole, like special acidities or the use of dangerous compounds. So to keep them stable, plants have to put them inside special compartments within the flower's cells called vacuoles. That way, the plant can adjust the pH, add metals or extra molecules, or do whatever it needs to keep those blue pigments happy without applying those same tweaks to the whole cell. Unfortunately for any would-be painters, that also means if you take the pigments out of the flower, they tend to lose their color really fast. But there are some solutions to the blue dilemma, like chromoproteins. These are proteins with color. Anthocyanins and biliverdins aren't proteins. They're complex molecules, but in the scheme of things, relatively small. Proteins are made up of chains of amino acids and are much larger, more complicated molecules than our other options. But turns out they can be a good way for life to imblue itself. The most notable blue chromoprotein life makes may be hemocyanin, the molecule that some invertebrates use to carry oxygen in their blood. It's the equivalent of our red-colored hemoglobin. And the difference is partly thanks to metals. Hemocyanin has an atom of copper, while hemoglobin uses iron. Horseshoe crabs, for instance, have hemocyanin in their blood, and it is a beautiful baby globin. And the difference is partly thanks to metals. Hemocyanin has an atom of copper, while hemoglobin uses iron. Horseshoe crabs, for instance, have hemocyanin in their blood, and it is a beautiful baby blue color. Another example of a chromoprotein is found in lobster shells. Lobsters get their dark bluish hue by taking two molecules of the normally red pigment astaxanthin and sticking them together. They are then bound up in a protein to create beta-crustacyanin, which is deposited in the lobster's exoskeleton. The protein parts form weak chemical bonds with the pigment, which act kind of like conjugation in that they lower the energy needed for the electrons in the normally red astaxanthin to jump state. states. That makes the complex blue. Fun fact, this is also why lobsters turn red when you cook them. The astaxanthin is freed from the protein as the protein part heats up and falls apart, and voila, you have a red shell. Crabs have a similar deal, and other blue chromoproteins exist in some mollusks and jellyfish. So while there are a few ways or blue and red form weak chemical bonds with the and bluish hue by taking two molecules of the normally red pigment astaxanthin and sticking them together. They are then bound up in a protein to create beta-crustacyanin, which is deposited in the lobster's exoskeleton. The protein parts form weak chemical bonds with the pigment, which act kind of like conjugation in that they lower the energy needed for the electrons in the normally red astaxanthin to jump states. That makes the complex blue. Fun fact, this is also why lobsters turn red when you cook them. The astaxanthin is freed from the protein as the protein part heats up and falls apart, and voila, you have a red shell. Crabs have a similar deal, and other blue chromoproteins exist in some mollusks and jellyfish. So while there are a few ways organisms have solved the blue pigment dilemma, it ends up being a lot of hoops to jump through. Compare this to structural blues, which are complex in their own right, but often made of relatively easy to make building blocks like collagen. So you don't have to use toxic substances, nothing that could potentially interfere with the functioning of a cell. To be clear here, we're not saying organisms considered their options and went with structures over pigments. Rather, over the course of evolution, they were just more likely to stumble on a blue structure rather than a blue pigment, given all of the constraints on blue pigments. Which actually brings up a pretty decent question. Why go to the trouble of having pigments at all? Why do we have so many red and yellow pigments? After all, the molecules in structural colors are cheaper to make and more stable, since they aren't absorbing light energy all the time. This is literally why colors fade in sunlight. The light energy molecules absorb can sometimes break them, splitting the molecules apart or twisting them into new colorless forms. So you also don't have to worry about structural colors fading. But in a poetic turn of events, while it's easy to make structural blue and hard to make chemical blue, it turns out it's actually really hard to make structural reds. You can get reds with iridescence, where the color changes depending on the viewing angle. Think of a blackbird's wing or an oyster's shell. But it's much harder to create a pure red because blue light creeps in and pollutes it. Yellows and oranges are really hard too. So blue is actually kind of special in that you can employ structural color to get vibrant blues. So to recap, it is hard for life to make blue pigments because it's hard for life to make the right kind of molecules. They're often big or need a lot of help or require some cellular shenanigans to work right. Scientists are continuing to look for new blues, of course. We found a lot of exciting blues in the ocean, for instance, in the marine life, not in the water. To be clear, we know the water is blue. That's structural, actually, not pigment. And we're not gonna open that whole can of worms because I think we already have an episode on it. And finding and understanding these pigments could help us create better or more environmentally friendly paints and dyes. But also, it's amazing to look at the rainbow of colors life gives us and then be able to point to just one of them, just the blues, and say, you know, this one's special. Before we go, I wanted to talk about the Awesome Socks Club, a thing that my brother John and I are starting, which will definitely not give you the blues, unless some of the socks are blue, which I think that they will be. This is your way to dress up your feet with 12 unique, snazzy designs, each created by a different designer every month of 2021. And 100% of after-tax profits will go to decrease maternal and child mortality in Sierra Leone. So your fancy feet will be helping other people too. But the catch is, you have to order by December 11th so we know how many socks to make. So go to awesomesocks.club/scishow to learn more.
친환경 슈퍼모델
Shut up.
Thanks to Brilliant for supporting this episode of SciShow. Go to brilliant.org/scishow to check out their course on infinity. Imagine you're walking along a rocky beach when, out of the blue, you see this forearm-length fish charge straight into the shallows. We're talking water that's less than 10 centimeters deep, where a fish that big could easily end up beached. After a moment, the animal kind of flops its way back into deeper water, and then it does it all over again. This is exactly what fish researchers saw off the coast of Saudi Arabia in May 2018. So they started recording. And it turns out it wasn't just any old fish, it was a Titan triggerfish, a voracious and smart marine hunter. And what they had witnessed was the animal flexing its brain power to snag crabs from the shore. Venturing into very shallow water might seem like a poor choice for any fish, but that triggerfish was no fool. It had spotted a tasty treat just out of its reach, so it figured out how to reach it. Which might sound pretty clever, because it is. And it's right in line with what ichthyologists know about triggerfishes. For example, in the 1970s, German biologist Hans Fricke tested the problem-solving abilities of 3 yellow-spotted triggerfish he decided to call Odonis, Flip, and Berta. He showed Odonis a delicious sea urchin and then put it in a glass dish under an opaque lid. And it didn't take the fish long to suss out the new materials and solve the problem to reach the treat. So Fricke stepped up the difficulty. This time the urchin went under a mesh container that had to be lifted or tipped. Then he let Flip and Berta have a go at it. Once again, the fish got their rewards, but each solved the problem slightly differently. And they remembered what they learned. When he moved the set to a new area and retried the test, they both reached the urchin much faster. To Fricke, that indicated they were smart enough to generalize their knowledge to new scenarios. On other dives, Fricke observed what appeared to be evidence for social learning in a different triggerfish species. In other words, the fish seemed to learn from one another. He came across 5 different individuals in a small area that all ate urchins in a totally unique way. Instead of flipping them over with jets of water like most triggerfish, they first bit off the spines, then hauled the urchins up towards the surface so they could nibble at the soft undersides as the denuded animals fell. It seemed unlikely that each of them figured this out separately, so he concluded it was probably one fish's idea, and then the other 4 watched and copied the behavior. Now, the researchers aren't sure if the beaching triggerfish they saw figured out its clever hunting tactic all by itself or learned it from another fish. But no one has reported anything like it in any triggerfish species. And either way, it shows that the Titan has some pretty impressive smarts. And that may be because it's got a big brain. See, the part of the fish brain called the telencephalon is relatively large in triggerfishes. And studies have linked larger telencephalons with better problem-solving abilities, at least in some species. Researchers have even suggested that if we really want to understand how cognitive abilities evolve, we should study fish instead of the, quote, smarter animals like primates. That's because fish are much more varied in their abilities, environments, and social interactions than primates are. So the clever tricks of triggerfish aren't just cool to watch, they could also help teach us a lot about how intelligence evolves. And if all this talk of problem solving and intelligence has you eager to add to yours, you might want to check out the STEM courses offered by today's sponsor, Brilliant. They have more than 60 of them, and they cover everything from algebra to cryptocurrency. And they're all really fun since they're packed with problems to solve and even code writing. Take their new course on infinity, for example. In it, you build up from counting to understanding the uncountable through exercises and stunning visualizations. You can take it and all their other courses when you sign up for a premium subscription. And right now, if you're one of the first 200 people to sign up at brilliant.org/scishow, you'll get 20% off. So check it out if you're interested.
When we want to see more clearly in the dark, we shine a light, because light helps with seeing. But we're not the only species that does this. Some fish have evolved a nifty trick called active photolocation, which is a fancy way of saying they can shine lights to see better. Now, most predators find it a whole lot easier to catch things when they can see them, but even with great eyesight, seeing isn't always easy, especially when you live underwater. Water is often murky, and more to this point, it filters out light, so the deeper you go, the darker it gets. That may be why the only non-human animals we know of that can perform active photolocation come from the sea. Take black-faced blennies, for instance. These little fish can't make their own light, but they appear to manipulate the light from the sun. Thanks to the spherical lens covering their eyes, some of the sunlight from above misses their pupils so it doesn't go into their eyes. Instead, it bounces off mirror-like spots that sit just underneath them, generating a sideways beam of light known as an ocular spark. Studies suggest the fish can direct this spark to help them find prey, as many undersea creatures have eyes that reflect light, much like a cat's. And they can probably turn this spark on or off or even change its color through small eye movements that slightly redirect the sunlight. Some of the below pupil spots contain a blue pigment, so when sunlight hits there, only blue light is reflected outward. Others contain fluorescent compounds that absorb blue light and emit lower energy red light instead. So when sunlight hits them, the fish emit a red spark. And studies have shown that the spark color changes depending on the background the fish are looking at, which makes sense since it's kind of useless to look for blue light bouncing off things if everything looks blue. That may
Wait. What else do I have? Garage Titania Harrow. Wait, Gara? Gara. Did I not? Did I not make Gara? Wait, yes. Farming Niger should be bad. And Raj. Wait, what happened to Kara? Kara. I don't think I subsumed Kara yet. God.
May actually be why they need the spark in general, because their favorite food does a great job blending in. They snack on tiny critters that are easily mistaken for algae, but algae don't have reflective eyes, so shining lights at potential meals can help the fish separate yummies from seaweed. These ocular sparks may also help them spot predators. When researchers gave fish little light-blocking caps, they struggled to avoid predators lying in wait for a snack. Ocular sparks are so useful, in fact, that these blennies might not be the only fish to have them. Researchers think the phenomenon may have been overlooked because it happens on a very small scale, and they only discovered it in the past few years. We know a lot more about really obvious shiners, like flashlight fish. That name pretty much speaks for itself. They have a bean-shaped organ underneath each of their eyes that shines light. But since they hunt at night, they get no help from the sun. Their light comes from symbiotic bioluminescent bacteria instead. These helpful microbes live in the fish's under-eye organs, and they generate a blue-green light with a wavelength of about 500 nanometers, which conveniently travels farther underwater than other visible wavelengths. Each organ is essentially a pouch with a big mirror in the back that directs light outward, and it's connected to the edge of the fish's eye in such a way that they can turn the light on and off by blinking. These fish likely light up their prey's eyes in order to find them too. Their flashlights come in off by blinking. These fish likely light up their prey's eyes in order to find them too. Their flashlights come in handy for communicating with one another and maybe even for evading predators. But they're not the only group of fish with blue flashlights. The appropriately named lanternfish also have them, and so do dragonfish. As their name implies, they're ferocious predators with loads of pointy teeth. and they too sport blue light producing organs right behind each eye. Even more impressively, they make that light themselves without the help of bacteria. But just to make things a little creepier, at least 9 deep-sea species also have organs under their eyes that emit red light. This light starts out the same blue that shines from behind their eyes.
Oh. Wait a second.
But then it hits fluorescent pigments that absorb it and re-emits it as red light. Some species even have a filter on top of this to ensure that they shine out at a very specific wavelength. Why go through all that extra effort? Well, red light is the first color to disappear as you dive deeper underwater because it carries the least energy of all visible wavelengths. That means it never reaches the deep sea, so most of the species there have ditched their ability to see reds over evolutionary time. Not the dragonfish, though. Some species have special light-sensitive proteins in their eyes that detect it. Others use a special pigment that acts like and comes from chlorophyll, the main pigment plants use to harvest light energy. This modified pigment is able to absorb red light energy and transfer it to the fish's other light-sensitive proteins, broadening their visual range. And since, down in the deep, pretty much only other dragonfish can see red light, they can shine it at whatever they want without alerting prey or predators. They basically have built-in night vision. Studying them and all these other flashlight-wielding fish can teach us about the complexities of vision, especially underwater. And that, in turn, could help us and our machines see better, beneath the waves, and in general. Plus, the more we learn about fish eyes, the better we'll understand fish behavior and ecology. So you could say all this research on active photolocation is really shining a light on evolution in the murky depths. I couldn't resist. If all the talk about dragonfishes and their glowing red eye lights wasn't quite enough nightmare fuel for you, I'd recommend watching our episode about their teeth. And be sure to subscribe and ring the notification bell to keep learning about this bizarre universe with us.
Humans have been trying to control the weather since ancient times, but even with modern technology, we can barely even predict the weather, let alone manipulate it. At least on purpose, because it turns out there are quite a few ways that humans do influence the weather, and not just through climate change. Even on local levels, human activity can produce more rain. Most of the time, it is by accident, but purposely increasing rainfall might not be as far-fetched as it sounds either. Some of the biggest markers of human activity are cities, where people have drastically altered the landscape to fit lots of living and working spaces all in one place. And research has shown that compared to the areas around them, cities get more than their fair share of rain. One big reason for that is urban heat. Cities tend to be a few degrees hotter than their surroundings, thanks to a number of factors. For one, they're full of heat-absorbing materials like concrete, asphalt, and steel. Then there's all the heat-producing machines like cars, air conditioners, and heaters all stuffed into a small area. And since dry, flat surfaces like rooftops and roads have replaced a lot of the natural vegetation, there isn't as much shade or natural cooling. So you get what's called an urban heat island. And thanks to all that heat, water molecules on the ground have more energy, so they can more easily break the hydrogen bonds that hold them in their liquid form and turn into vapor. As a result, there's extra water vapor in the air over these urban heat islands. And that sets off the process of forming rain, because rain forms as water vapor in the atmosphere condenses and forms little droplets. Once enough water droplets have come together, they get heavy enough to fall out of the cloud. So the more water vapor there is in the air, the more easily that happens. As a result, in cities and the areas temperatures around them, rainfall is both more frequent and more intense. Like one study of cities around the world found that downwind of cities, the average rainfall was as much as 50% greater than it was upwind of cities. And a recent study in the Eastern Mediterranean found that for each degree Celsius the temperature rises, there's around a 3% increase in the intensity of rainfall. But urban heat isn't the only reason cities produce excess rainfall. The jagged landscape full of skyscrapers and other buildings also plays a role. That's because as air flows into a city, it slows down as it encounters tall buildings and gets trapped in place. So as more air sweeps across the land or water and comes to a halt over the city, it creates a kind of pileup called convergence. As the relatively moist air hanging over the ground gets forced upward, it delivers extra water vapor to the clouds. Once again, as that water condenses into droplets, it can eventually fall back down as rain. And there's another way cities can create convergence too. In some cases, they can slice storms in half, sending clouds flowing around the city, a lot like a rock splits the flow of water in a creek. And when the parts of the storm recombine downwind of the city, the colliding air can get pushed up again, producing more rain clouds and making the storm more intense. But cities don't just make storms rainier, they can also make storms longer. Thanks to all those tall buildings creating friction with the air, storms that roll in and lose their momentum can get stuck in the city. Researchers think that's what happened when Hurricane Harvey struck Houston in 2017 and dropped rain on it for days. Simulations have suggested that friction from Houston's buildings slowed down the storm enough to increase rainfall by up to 50%. Now, it could be hard to say exactly how much of a role humans play in specific rainfall events because weather is an unpredictable and complex thing. But by looking at broad weather patterns, we can see our impact more clearly. And in one incredible study, researchers studied old weather patterns to show that humans have increased rainfall by testing nuclear bombs. Scientists had suspected for a while that nuclear bombs might influence rainfall because radioactive decay floods the atmosphere with electric charges. And even though water molecules don't have any overall charge, there's a slight difference in electric charge across each molecule. So when there are other charged particles in the air, the oppositely charged side of the water gets attracted to them. Pairing up with these electric charges basically accentuates water's slight charge difference and helps droplets stick together more easily. And just like in the first two examples, the more droplets stick together, the heavier they get, making them more likely to fall to the ground. But in practice, scientists weren't sure how significant this effect would be. So authors of a 2020 study published in the journal Physical Review Letters found a clever way to work it out by using historical weather data to investigate the impact of nuclear bombs on rainfall levels. They gathered the data from a weather station on a remote island in northern Scotland where there was very little pollution to interfere with their results. First, they looked at data documenting the amounts of various particles in the atmosphere during the nuclear testing of the 1960s. The data included information about levels of the long-lasting radioactive element strontium-90, which is produced in nuclear reactions. The researchers found that those levels peaked around 1962, and the levels of charged ions in the air peaked with them. Both levels then dropped a few years later after a treaty was signed in 1963 that reduced the amount of above-ground testing. So then the team looked at historical weather data and found that before and after the treaty, rainfall and cloud cover in the region also changed. In particular, during the years of heavy nuclear testing, the cloud cover was thicker and the rainy days were extra rainy. They had about 24% more rainfall than usual. Now, these findings weren't totally surprising. They supported scientists' long-standing theory about how electric charge influences rain. But what's incredible is that this weather station was thousands of kilometers away from nuclear tests. In other words, bombs dropped in Nevada and Kazakhstan had an impact on the weather in Scotland for years. But it does not take nuclear fallout to change the atmosphere in ways that make rain. Ordinary aerosols have been doing it for ages. Now, an aerosol can be a lot of things. Technically, it refers to any fine particles suspended in air, both natural and human-generated. It includes things like volcanic ash, as well as pollutants from cars and factories. All these things can act as a nucleus for water vapor to condense around, because when water condenses in the atmosphere, it always does so around some kind of particle, like dust, which is known as a nucleation site. So when there are more particles in the air, water vapor condenses into a bunch of different droplets. If they're light enough, the droplets won't always fall, which is why most of the time aerosols actually reduce rainfall. The water vapor gets spread out so thinly among all these little particles that the droplets that fall from the cloud are really tiny, and they end up evaporating before they reach the ground. Plus, aerosols can darken the sky and cool down the air, which produces the opposite effect of the urban heat island. But researchers have proposed that under the right conditions, aerosols can increase rainfall too. If a cloud has lots of water vapor to begin with, then there's enough of it to go around to all the nucleation sites. In that case, the fact that there are more possible nuclei just means more droplets can get big enough to fall as rain. So rainfall may end up being more intense than it would have been otherwise. In general, although humans definitely do make it rain, it's usually by accident and not really under our control. But for our last example, we will look at one way people have been trying for decades to make rain or snow on purpose. It's called cloud seeding. The key to cloud seeding is the fact that, like in the last example, water needs some kind of nucleus to latch onto before it can form droplets or ice crystals. And in the 1940s, a pair of scientists wondered if they could get more water molecules to turn into snow and ice by adding lots of extra nucleation sites to clouds. They tried it out in the lab using silver iodide to turn cold water vapor into snow, and they actually had some success. But it's a hard idea to test in the real world. Like, how do you know it wasn't gonna rain anyway? Plus, you can't exactly repeat the experiment because weather is too weird to have the exact same conditions on any 2 days ever. But the idea has still attracted a lot of attention. Various researchers have come up with other materials that might act as nucleation sites for ice or rain, like dry ice or salt, and others have even put it to the test. Like in the 1960s, the US government actually tried to weaken tropical storms through cloud seeding in an effort called Project Storm Fury. They thought that by seeding clouds near the eye of a storm, they might be able to make the eye grow, which they hoped would slow down wind speeds overall. That didn't work, and later research into hurricanes showed that the idea was flawed even in principle. But in 2018, scientists finally made a breakthrough when they directly observed cloud seeding in nature for the first time. They sent 2 planes to inject silver iodide into clouds over Idaho and used radar to watch the snow form. Unfortunately, even though this experiment seemed to demonstrate true cloud seeding, we are still nowhere near any kind of useful cloud control. We're not going to be able to make rain over a cornfield or drain a cloud right before a sporting event anytime in the near future. There are just so many factors that go into determining whether a cloud will unleash a torrent or a drizzle that it's hard to manipulate the process. But if there's one thing to take away from this video, it's that humans can make huge impacts on the planet we live on, for better or for worse. And the better we understand that power, the better decisions we can make about how to use it. Thanks for watching this episode of SciShow, and speaking of rain, if you've ever wondered what it actually means when the forecast predicts a 50% chance of rain, we have an answer for you, and you can catch our episode on that next.
Thanks to Brilliant for supporting this episode. Go to brilliant.org/scishow to check out their Practicing Infinity course. Animals have a lot of different strategies for getting themselves out of tight spots, but most of them involve evading capture, because there's just not a whole lot you can do if you've already been eaten. Unless you're this particular type of water beetle. Regimbardia attenuata is a water scavenger beetle found all across the eastern half of the globe, from Australia to Japan to the Arabian Peninsula. It's small, dome-shaped, kinda cute, but it didn't get a whole lot of attention until biologist Shinji Sugiura fed one to a pond frog and then watched it crawl out the other end. And it wasn't a fluke either. He's since discovered that 9 times out of 10, this particular brand of beetle makes its way out of a pond frog's digestive system alive. And at least 2/3 of the time, these beetles escape the digestive tracts of 4 other frog species, although the success rate seems to vary a bit depending on the frog. Now, the first thing you've got to wonder is if these beetles are actively trying to escape, or if they're just waiting around until they get pooped out. Sugiura wondered that too, so he devised an experiment. He used wax to glue together the legs of some unfortunate beetles so they couldn't move, then fed them to the frogs. Spoiler alert, the beetles died. Also, it took a long time for them to reappear, like more than 24 hours, while unglued beetles generally made their escape in less than 6. One was even observed exiting after about 6 minutes. Maybe it wasn't his first time? Anyway, this seems to confirm that the beetles are actively escaping. But while their survival seems kind of miraculous, it's probably evolutionary luck. Regimbardia attenuata is an accomplished swimmer, so once inside a frog, it just keeps doing what it does best. It also has its own personal scuba tank. It stores a bit of air under its exoskeleton, so the oxygen-free environment isn't a problem either. And water beetles are kind of naturally watertight, so that hard armored shell probably gives it some protection against the frog's digestive juices. But then there's that final, seemingly insurmountable barrier, the frog's sphincter. The beetles aren't strong enough to force the opening, still they seem to know what to do. You see, the beetles always come out head first. So researchers think that they're mechanically stimulating the hindgut to induce the frog to poop. You know, just like this talent for surviving digestion isn't totally unique in the animal kingdom. Some snails can make the trip through a bird's gut, and some fish eggs may occasionally survive too. But they're not quite as good at it. According to experimental studies, only about 15% of snails make it through alive, and less than 1% of fish eggs do. Plus, they don't play an active role in their eventual escape. Interestingly though, when scientists tried other beetles from the same family, they all got digested. Still, it's likely Regimbardia attenuata isn't the only water beetle that survives digestion. Most humans don't spend their downtime looking at frog butts, so we may be missing the evidence for this weirdly effective survival strategy in other species. Or maybe the other water beetles are just like, nope, digest me already. I draw the line at sphincters. Anyway, that's all I've got on water scavenger beetles, so it's time to give a quick shout out to today's sponsor, Brilliant. They offer dozens of courses that can help you broaden and deepen your STEM knowledge on your own time and at your own pace. Like their newest course on infinity helps you wrap your mind around the idea of endlessness. And with their iOS and Android apps, you can take the learning with you wherever you go, even offline. So you can expand your horizons and your mind at the same time. You can learn more at brilliant.org/scishow, and the first 200 people to sign up for an annual premium subscription there will get 20% off. So check it out if you're interested, and thanks for watching SciShow.
Hi everyone, my name is Denise Ruffner. I'm VP of Business Development at INQ.
Hello, Christopher Savoy, CEO and founder of Zapata.
The quantum world is weird. Physicists have a pretty good handle on it mathematically, but that math can sometimes point to things that just seem wrong. Like a particle zooming towards a seemingly impenetrable barrier and then just poof, appearing on the other side. Yet, not only does this happen, it's essential for things as fundamental as photosynthesis and solar fusion, aka how the sun makes light and heat. Physicists call this phenomenon quantum tunneling, and for a long time, they've argued about the details behind how it works. Like, do particles spend time in the barrier, or are they somehow teleporting straight across it? Now, though, there's finally some hard evidence, and it seems like quantum tunneling can actually be kind of slow, at least by quantum standards. To know how tunneling works, it helps to know a little about quantum physics in general. In the world of the really tiny, physicists use a mathematical function called the wave function to describe the properties of particles. For instance, if you're looking at an electron, its wave function would describe where it is, how fast it's moving, and so on. And one way we can use wave functions is in the Schrödinger equation. This takes a wave function and uses it to predict what will happen to a particle next. If you're familiar with Newton's laws of motion, it's like those, but for the ultra-microscopic. Now, what exactly a solution to the Schrödinger equation means has been debated for decades. But here, just know that most physicists agree that the resulting wave function is a description of the probability of finding an object in a given place at a given time. The wave function is, well, a wave. so it can be larger at some points and smaller at others. And the bigger the wave is at a given point, the more likely your object is to be in that place when you look for it. Even the location of large things like you and me are theoretically described by these waves, but the effect is way too small to be measurable. But with really small objects, on the scale of a few atoms, this becomes super important. So coming back to quantum tunneling, one way waves get weird is when they approach obstacles. Waves, even familiar ones, have a kind of curious property. They rarely stop dead in their tracks when hitting something. Like, think about sound. If sound waves were perfectly blocked by solid objects, then the inside of your car would be a zone of complete silence, even if someone was jackhammering the sidewalk next to you. And all that sunlight hitting your windshield would just stop, leaving you in total darkness. The same basic idea is true for the wave functions that describe quantum particles. An object's wave function can extend into or even past an obstacle. And since that function describes the probability of finding a particle in a given location, sometimes the particle ends up there too. That's quantum tunneling in action, and it's as strange as it sounds. Physicists discovered that electrons could do this in 1927, in the very early days of quantum mechanics. And ever since, they've wondered what objects do while they're tunneling through the barrier. And like, how long does tunneling take? Some researchers have argued that it's instantaneous. Others have wildly different ideas. Well, a team at the University of Toronto went on a 20-year quest to find out and published the long-awaited results in the journal Nature in July 2020. In their experiment, they sent atoms of super cold rubidium to tunnel through a barrier that normally should have reflected them. When you're dealing with individual atoms, you need incredible precision, so the researchers used laser beams instead of a physical obstacle like a wall. They used one beam to control the motion of the atoms and a second to act as a barrier for the atoms to tunnel through. The choice of rubidium also wasn't random, because rubidium has an interesting property. Its spin can be altered by lasers. So in the study, when the atoms passed through this laser barrier, their spin would change. And the longer this took, the more their spin was affected. To be clear, spin doesn't actually mean rotation, but the details are messy enough that even the researchers have referred to it this way. So here, it's a fine approximation. The larger point is, by measuring the atom's spin axis before and after they entered the barrier, scientists could tell how long the atoms took to tunnel. And their final result was an average of 0.61 milliseconds, which, sure, is silly fast considering a blink of an eye is a few hundred milliseconds, but it's also pretty long for something that some people have suggested is instantaneous. Now, none of our current technologies actually use rubidium atoms or lasers like this, so the actual number is less important than the fact that it was possible to measure it. But measuring it at all is a big deal, because knowing how long quantum tunneling takes could be really useful not just for understanding the world, but for building newer, better technologies. Like, quantum computers aren't quite ready yet, but in theory, they have the potential to process more information than we could ever imagine. Except these devices work by timing and tracking individual particles, so if you don't know how long tunneling takes, it can be hard to plan what your computer will actually do. So this measurement is a key step in resolving an argument that's been raging for almost a century, but it also has the potential to unlock a new world of awesome tools. Thanks for watching this episode of SciShow. We're only able to talk about complicated quantum topics like this because of our amazing patrons on Patreon. Their support allows SciShow to keep exploring the universe and share all the things that we find. So to our patrons, thank you. And if you're not a patron but want to learn about becoming one, you can do that over at patreon.com/scishow.
When we want to get from point A to point B as fast as possible, we take to the air. But humans are newbies in the world of flight. While we've had commercial flights for over a century, other animals have been flying for millennia, and for good reason. From an evolutionary perspective, flight is awesome. Animals do things a little different from us though. So today, we're going to look at the bizarre world of animal flight, from birds to bats to spiders and snails. Oh, come on.
sanctuary will go on without you.
Come on, now you're really making stuff up. Flying snails? All right, I'll wait for it. Let's kick things off with the undisputed champions of the air. Birds. These living dinosaurs constantly dazzle us with their aerial acrobatics, so naturally, we've looked to them for tips and tricks. For instance, fighter pilots often fly in a V shape, an idea we humans totally stole from migrating birds. But not all birds fly in Vs, no matter how far they're flying. Why not? Here's Hank to explain.
Think of a flock of birds, and you probably imagine that classic V shape, a leader with sets of trailing birds on either side. But not all flocks fly this way. Starlings, for example, travel in large, three-dimensional clusters that seem to move like a wave. So, why do some species fly in Vs and others in clumps? Well, it turns out it has a lot to do with the individual birds themselves. Some, like geese heading south for the winter, are making long treks. The V formation helps them stay in visual contact with each other, avoid collisions, and conserve energy. It's the structure of their wings that lets them take advantage of the V. As the wing flaps, each wingtip creates a vortex that spirals up from the bottom of the wing and over the top. This vortex trails off behind each bird as it moves forward and is encountered by the next one in the line. The trailing bird positions itself to catch just the upwash of that vortex, or the upward force, and that requires being behind and just to the side of the leading bird. Lots of birds behind and to the side of one another creates that V shape. Studies have estimated that birds flying in this way can save around 15% of their energy. So, why don't all birds fly this way? We talked to Professor Eric Green from the University of Montana Bird Ecology Lab, and he explained that this has to do with the size of the bird. You may have noticed that birds that fly in a V, like geese, pelicans, swans, and ibises, are typically larger creatures with a long wingspan. These species move their wings only a few degrees up and down with each flap. This motion creates vortices that lie pretty neatly behind the bird. Small birds, on the other hand, tend to flap their wings all the way up and down. The vortices created by these motions are all over the place, not consistent enough for their flock mates to actually use. And the small birds that do flap their wings like larger ones just don't generate a big enough vortex because of their size. For small birds, flying in groups sometimes uses even more energy, not less. But these species have another need that's even more important: protection. In 1971, evolutionary biologist William David Hamilton proposed a theory called the selfish herd. It suggests that the risk to an individual is reduced if that animal places another animal between itself and a possible predator. Repeat this across enough individuals, and you end up with a herd, or in this case, a flock. Other theories offer similar explanations, but whether you're talking about schools of fish or swarms of insects, it's clear that this is a pretty common survival strategy. So the next time you see a group of birds flying by, you'll know it might be to save energy, or it could just be to stay alive.
McDonald's kitchen story. First, make sure the juice is kept well inside.
I just had a weird thought. Can you imagine if we flew planes in flocks? That would be a logistical nightmare. No wonder we don't mimic everything birds do. And actually, now that I think about it, there are other aspects of bird flight we don't usually copy, like their flat tails. Our planes have vertical ones. Is that because we're better at flying than birds? Stefan, what do you think?
I don't know if you noticed, but
Nature's kind of awesome. That's why so much of our technology is inspired by it, from adhesives modeled after insects to early plane wings based on birds. But just because we try to mimic nature doesn't mean we can do it perfectly, and birds and airplanes are a pretty good example of our limits. Take the vertical tails on most airplanes. We use them to keep our giant metal contraptions in the air and going the right way. But birds get by fine without them. That's because they're just way better at flying than we are, and for the most part, we can't keep up. The parts of an airplane all work together to keep the plane in the sky and facing the right direction. But thanks to all kinds of invisible air currents, that isn't as simple as it looks from your window seat. The vertical tail's main job is to stabilize something called yaw. Yaw measures how much the plane is pointed to the left or right of the wind, specifically the relative wind, which is created by the plane zooming through the atmosphere at hundreds of kilometers an hour. Yaw can change in lots of situations, like during turns or in unsteady air. And when it does, it occasionally leads to a condition called side slip. This is where the plane has yawed, but it hasn't completely changed its direction. Instead, it's still mostly moving in the direction it was, only at a funny angle. Kind of like a sports car drifting around a turn. Normally, this just leads to a little inefficiency, but if it's not corrected, side slip can get out of hand. If the plane yaws too much, it starts to affect how the air flows over the wings, and if too much air flows parallel to the wings instead of perpendicular, the plane can lose lift, which is kind of important for keeping it in the sky. That's where the vertical tail comes in. See, as the plane starts to side slip, the side of the tail will start to face into the relative wind and become more perpendicular to it. And as the wind pushes on the tail surface, it creates a force that ultimately nudges the whole plane back to face its original direction. Birds, meanwhile, don't have to deal with all of this because they're way better at flying than we are, which kind of makes sense. They've had millions of years to work on it. They don't need vertical tails for stability because they're constantly making fast, tiny adjustments to the shape and angle of their wings, which lets them avoid side slip. Right now, that's just not something we can practically or easily do with airplanes, especially passenger jets. And even though there have been some planes without vertical tails, like the B-2 stealth bomber, they come with plenty of stability challenges. So engineers are definitely working on it, but it looks like nature has us one-upped for now.
Our Earth is like...
That figures. Birds have been flying for millions of years. Of course they're better at it. And there's still a ton they can teach us about flight. In fact, researchers are actively trying to apply what they're learning from studying birds and other animals to our flying contraptions. So here's Michael with 3 ways nature is inspiring drone engineering.
Drones are awesome, but they could be even better. Like, they're kind of hopeless in smoke or fog, and they're just so big. I want a drone that fits on my finger like a bug. That kind of thing is exactly why engineers have been turning to nature to perfect drone tech. After all, animals have been flying for more than 300 million years, so they've got a bit of a head start on us. And we can learn a lot from them about navigation, miniaturization, and even the best color to be for optimal flight. It's not hard to imagine a situation where it might be helpful for a drone to have an idea about what's around it. Like, imagine if a drone could find its way through smoke-filled rooms in a burning building. It could help emergency workers save lives by scanning areas where people might be trapped. But smoke makes it pretty hard to see anything because the small particles bounce visible light all over the place. And it's not just smoke. Fog, snow, dust, anytime you have lots of light-scattering particles, it can be pretty tricky to see where you're going. Even some radar gets stumped. So, to help drones navigate these conditions, scientists are studying animals who see with more than their eyes. Echolocators like bats map their environment based on how long it takes a sound to echo back after they make it. Sound is a pressure wave, so it mainly moves through the air around particles instead of getting bounced. But while a couple of scientists have made drones based on bats, bats are pretty hard to mimic. They're smaller and more maneuverable than a lot of today's drones, and bats have evolved a ton of really specialized structures in their brains and bodies that are great for echolocation, but aren't easy to recreate. So another team of scientists looked at oil birds instead. These South American birds use echolocation to find their way around caves, but they're bigger than bats, and their echolocation isn't quite so sophisticated. Plus, they use their talents more sparingly. When there's a lot of light, they mostly use their eyes. Then when it gets darker, they switch to their ears more and more. And that kind of switching between systems is exactly what you'd want in an autonomous drone. But it'll probably be a little while before any oil bird-inspired drones hit the market. Researchers still need to figure out how the birds' brains combine all this information to create a single picture of the world, because that's what drones will need to do before we can let them fly by ear. Now, one of the upsides to oil birds is that they're already about the same size as modern drones. But one of the big goals of drone tech is to go small. The problem is, really small drones can't fly in the same way that big ones do. because physics. Today's drones mainly have fixed wings like planes or spinning blades like helicopters. But once fixed wings and blades get down around a few centimeters long or less, they stop generating the lift needed to stay airborne. Air just doesn't really glide around small things like it does big ones. Instead, it piles up, and little random differences in pressure from one place to another push objects around, destroying any lift they get from moving through the air in the first place. But we know small things can fly because insects exist, and researchers are learning from them how to miniaturize. Insects don't use rotary blades for wings, for example, and their wings don't stay still either. They're constantly flapping during flight, and the smaller they are, the more they flap. Flapping wings are just better for flying at small sizes, where flying depends on pushing against the air instead of gliding through it. So engineers have built little flappy drones modeled after little flappy insects. They're still working on efficient batteries for something so tiny, and they're still trying to make their little mechanical insects as stable as actual insects are. But they imagine a future where tiny drones can do things like precision pollinate crops. We could try to train bees to do that, of course, but it turns out they don't always listen when we tell them what to do. And who can blame them when they look so cool in those classic black and yellow outfits? Though bees do come in different colors, and so can drones. It turns out that different colors don't just make your drone look cool. Studies on animals suggest they might actually help it fly. Right now, you can split drones into two broad color groups, black ones and not black ones, but they should probably all be black. You see, a lot of animals have what's called counter shading. They're light on the bottom because it makes them look more like what's above, and they're dark on top because it makes them look more like what's below. Or so everyone thought. But experiments with models of birds, dolphins, and orcas have all found that darker backs may be more than camouflage. Both in air and in water, they seem to let the animals move with less drag because of how dark colors absorb and radiate heat. They heat up faster from sunlight and transfer that heat to what's around them, which makes the air or water they're in thinner and easier to move through. So if you want a drone that uses as little energy as possible to fly, you should get one that's the color we all instinctively know is coolest, black. Also, if someone ever says you wear too much black, just tell them you want to be more aerodynamic.
Bug-sized drones would be pretty cool, but I wonder if we can find a way to mimic the flight of spiders instead. Yes, spiders fly. Some of them. And the way they do it is amazing. They use electricity. Hank, tell us more.
So you're walking along, minding your own business, when you notice something out of the corner of your eye. You look up. That's when you see thousands upon thousands of spiders on long silk balloons falling from the sky all at once. You've just witnessed one of the most incredible and terrifying natural phenomena on the planet. Spider rains. For a long time, scientists assumed that, like kites, ballooning spiders can fly because their silken threads generate enough lift to ride currents of air. But according to a study published in Current Biology this week by researchers at the University of Bristol in the UK, they don't actually need a breeze at all. It turns out spiders can fly using the electricity in our atmosphere. Spider ballooning was first documented by an English naturalist in the 17th century, and ever since, scientists have been trying to figure out exactly what they're doing and why they're doing it. A lot of the time, the ballooners are baby spiders looking for a place of their own to settle down. They can reach altitudes of almost 5 kilometers and fly for hundreds of kilometers. Talk about putting some space between you and your parents. But instead of loading up their Volvos and moving to Montana to take off, these spiders find somewhere high up, then stand tall, raise their rears, and emit thin, meter-long silk threads in the shape of a sail. When they let go, they're pulled into the air with surprising speed, even on calm days. And that speed is one of the things that's never quite added up with the idea that these spiders ride the wind. Biologists have seen spiders ballooning when winds are almost imperceptible, or even when it's raining. And the wind hypothesis doesn't explain how the spiders eject their silk so forcefully without the help of their legs, or how the strands maintain a fan-like shape without tangling. So the team from the University of Bristol decided to test something no one else had: whether the spiders can ride electricity. The idea that electrostatic forces provide the necessary lift has been around for centuries, but no one ever really looked at it. Then in 2013, a physicist from the University of Hawaii worked out some of the theoretical details. He released his paper as a preprint that was never officially published, but the authors of the new study thought it was worth investigating. The whole thing hinges around the fact that no matter what the weather is, there's a difference in electric charge between the ground and the sky that creates an electric electric field. So if the spider's silk picked up some of that static charge, those threads could be pushed by the electric field. Since like charges repel one another, the charge of the ground, or whatever the spider is standing on, would propel the silk out and up, and enough pushing could fling the spider into the sky. But since that 2013 paper was purely theoretical, the new study's authors decided to put it to the test. They took ballooning spiders and placed them on a small cardboard pedestal in a special chamber designed to have no electric field or air movement. Then they induced electric fields of different magnitudes and watched what the spiders did. Even in the complete absence of wind, the spiders began to get into that rump-raising position that sets them up for ballooning. And with a strong enough field, they started to spin silk and even flew. Once airborne, the researchers could make the spiders rise or fall just by turning the electric field on or off. An earlier study published just last month in PLOS Biology noted that these spiders seem to test the wind with their legs before they start to spin their silk sails. And this week's study found that the hairs on the spider's legs moved in response to changes in electric fields too. But those hair movements were different from the way they moved in response to wind, which means the spiders might be feeling around for both of those things. Riding electricity could explain some of the weirder aspects of their flight, like how they take off on seemingly windless days or in the rain, but most of the time air isn't completely still, so the spiders probably use a combination of electricity and wind to fly. There are still some parts of this left to figure out though, like how the spider's silk becomes charged in the first place, or whether they can control their flight to decide where to land. Learning more about how spiders fly can help biologists predict when they're going to do it and get a better understanding of their ecological needs. And maybe it will make it easier to predict those rare episodes of spider rain, because I don't know about you, but if 10,000 spiders are gonna land in my neighborhood, I would prefer to know that that's going to happen before it happens.
괜찮은 거 하나. 이번엔 무슨 수를 써서라도 찾아내겠어.
Well, I know what I'm having nightmares about. Speaking of scary things, let's talk about flying mammals for a moment. We've already learned how their ability to echolocate could help us make smarter drones. Well, echolocation probably evolved after flight, and after birds exploded in diversity and pushed bats to hunt at night. And it turns out that flight plays a pretty central role in another aspect of their lives, their immune system. Here's Stefan to explain what flying has to do with immunity.
1/5 of all mammal species today are bats. And that's pretty awesome because they help us out in all sorts of ways. Like, they pollinate a lot of plants, help regrow forests and control pests, and their poop is a pretty excellent fertilizer. Plus, they're just really cool. Some of them can sense magnetic fields or use sound to find their food, and of course, there's one thing that they all have in common. They can truly fly. They're the only mammals around capable of powered flight without the help of machines. But they're also somewhat notorious for something else, being flying sacks of germs. Now, you might have noticed that part with all the talk about zoonotic diseases that's been happening lately. Those are diseases that are passed to humans from other animals. And while bats aren't to blame for everything, they have played a role in the transmission of at least 11 viruses, probably 12 counting SARS-CoV-2. These diseases aren't the bats' fault, of course. If anything, they're ours. Research shows that disturbing animal habitats is usually what causes the transfer of a zoonotic disease to humans. Still, bats in particular do carry a lot of viruses, and that's because they have unique immune systems, which means we can learn a lot about these pathogens and their effects by studying bats. In fact, bat immune systems are so special that what we learn from them could someday help us treat a wide variety of conditions, from cancer to diabetes. And the kicker is, bats probably have weird immune systems because they fly. Unlike gliding, flapping flight requires a huge amount of energy. So bats have evolved ways to kick their cellular fuel production into high gear, mainly by putting their mitochondria into overdrive. Those are special compartments within cells that turn food into fuel. But there's a catch. When mitochondria convert nutrients into energy, they also create byproducts called reactive oxygen species. So basically, mitochondrial exhaust fumes in the form of really reactive molecules which contain oxygen. Now, these aren't all bad. The immune system uses them to rouse immune cells to action and kill bacterial invaders. But they can also cause a lot of damage. They can weaken cell membranes, mess with proteins, and even break DNA. and because of that, they play an important role in diseases like cancer and arthritis. Cells can try to keep them in check with antioxidants, compounds that essentially neutralize these overeager molecules. But those can only do so much, and when the balance gets out of whack, cells experience a condition called oxidative stress. This is when most of the DNA damage happens. So bats' supercharged mitochondria mean extremely high levels of oxidative stress, which in turn means constantly high levels of DNA damage. But since bats don't immediately get super cancer after their maiden flight, researchers have long suspected that they've evolved ways to protect themselves from all this flight-related damage. And a few years ago, genetic studies found mutations which boost their ability to detect and repair damaged DNA. Essentially, they've also turbocharged the mechanisms that prevent genetically damaged cells from replicating, which may also explain why they don't seem to get cancers very often. So, bats produce tons of energy without damaging their cells. Sounds pretty awesome, really. But there's just one small problem. DNA damage can also be a sign of a viral infection, because viruses need to hijack the cell's genetic machinery to reproduce, and that process usually involves some strategic snipping. So naturally, DNA damage triggers an immune response, inflammation. Essentially, when cells detect DNA damage or other signs of infection, they chemically call in white blood cells. These cells kill and destroy pathogens using a variety of genetic and chemical tools. And they also help control how the inflammation unfolds, like by bringing in additional white blood cells or switching some of them from germ killing to tissue repair once the invasion is over. This immediate or acute inflammatory response helps to get rid of the invaders and promotes healing. But remember, thanks to their supercharged mitochondria, bat cells experience constant DNA damage. They can repair this damage thanks to those advanced DNA repair tools, but the damaged DNA should still light an immune flare before it's fixed. So bats would experience super inflammation all the time. And prolonged, chronic, and systemic inflammation isn't so great. White blood cells and the processes they set in motion can be really destructive to the body's own tissues. In short, too much inflammation can lead to organ failure and even death. So flight should be a death sentence. Except bats have evolved some neat ways to knock down inflammation too. For one thing, they dampen the activity of sting proteins. These proteins are one of the ways mammalian cells trigger an inflammatory response when a virus is detected. Also, a genetic analysis of multiple bat genomes showed that they're the only mammals that completely lack genes for pie-hin proteins, another set of inflammation-triggering sensors activated by damaged DNA. And those are just part of the story. It will still be a while before we completely understand how bats prevent or dampen inflammation in their bodies, because it seems like every time they look, researchers keep finding more of these adaptations. So to recap, we know that to make sustained flight possible, bats have ramped up fuel production and DNA damage detection while dialing inflammation down to a 1. But we know that inflammation is one of the big ways the immune system fends off intruders. So doesn't that leave them open to all kinds of actual pathogens? And the answer is yes. Around the turn of the 21st century, scientists discovered that bats act as a reservoir for a lot of viruses that are extremely dangerous to humans. This includes filoviruses, which cause hemorrhagic fevers like Marburg or Ebola, and Henipaviruses like Hendra and Nipah, both of which can cause fatal brain infections. And of course, coronaviruses like SARS, MERS, and most likely the notorious new coronavirus that started the COVID-19 epidemic. And there's mounting evidence that bats were involved in transmitting these diseases to humans, either directly or indirectly, like by infecting farm animals. And bats are also suspected of having given us other diseases in the past, like mumps, measles, and hepatitis B. But here comes another magic thing about bats. Even though they're widely infected with notoriously deadly viruses, they don't actually seem to get sick from them. The virus can be found in their bodies, but they don't have any symptoms. As for how that's possible, well, we still have more questions than answers, but researchers have discovered a few evolutionary quirks about bat immune systems that help make that happen. In part, that's because active viral infections in bats tend to be pretty short-lived, thanks to their hypervigilant interferon production systems. Remember how we said DNA damage is a signal of infection? That's because viruses try to reprogram cells to create copies of themselves. But cells aren't sitting ducks during this process. In addition to calling out for help, which is that whole inflammation bit we discussed, cells have an internal defense mechanism. They can make a protein called interferon alpha, which activates genetic and chemical tools that reduce the virus's ability to multiply and spread. Every other mammal we know of switches their interferon system on when an infection occurs. But genomic studies suggest bat cells always have their interferon alpha genes activated. This drastically cuts down the time it takes to react when a virus is
present, so it allows bats to nip the infection in the bud before it becomes a full-blown disease. And of course, there's more. All mammalian cells contain an enzyme called ribonuclease L, which, when activated, chops up viral RNA to stop a pathogen from spreading. But in us and most other mammals, activating this enzyme takes a complex chain of steps, so it's not super quick. But bats, on the other hand, can activate it directly with interferons, drastically speeding up infection containment. Scientists also think this fast activation of ribonuclease L helps bats outsmart viruses that have evolved to inhibit the enzyme before it can be switched on, something HIV does in humans, for example. So basically, when bats do get viruses, they're able to quickly clear them out, for the most part. They can still fall prey to at least a few, like the rabies virus. And even quick suppression of a virus can mean it stays around in a group of bats. Bats tend to huddle close together when they roost. Plus, they fly around in the same areas as bats from other colonies, and they're constantly spraying snot and saliva everywhere when they echolocate. So there's a good chance that during that window when a bat has a virus that is actively replicating, it will spread it to another bat. That means that even if each bat only hosts a virus for a short time, it can linger in the population. And even this probably isn't the full picture. Mathematical models indicate that by themselves, bats' social habits don't completely explain why they host so many viruses. Instead, research suggests that the viruses themselves have figured out how to lie dormant and undiscovered, like in the bat's lungs, spleens, or intestines. And then when the bat gets stressed, like when it's roused from hibernation, that stress temporarily dampens its antivirus systems, allowing any hidden viruses to emerge. This leads to another period of increased viral replication and shedding, so again, the bat can transfer the infection to other animals. Then its antiviral systems get back up to speed, and the viruses are eliminated or driven back into hiding. Still, even when a virus is replicating and being shed, bats don't generally seem sick, not like a person would with the same virus. And that's likely because their inflammation dampeners are still running. So they're still suppressing a lot of the immune responses that would make them noticeably sick. And that may also be why viruses that are deadly to us aren't lethal to them. It turns out that the most severe symptoms of illnesses like MERS and Ebola, the symptoms usually responsible for their lethality, aren't caused by what the virus itself does to the body. Instead, they're the result of the destructive, catastrophic inflammation the virus triggers. This includes an extreme systemic reaction called a cytokine storm, where an over-release of pro-inflammatory signaling proteins turns a person's own immune system into their worst enemy. And some researchers think that our aggravated inflammatory response may actually be because these viruses have evolved to dodge the super-refined immune systems of bats. Basically, they evolved to survive in a host that constantly and aggressively attacks their ability to replicate. So when that assault is suddenly weaker in a new host, they go wild and produce a lot of little virus babies that send the host's immune system into panic mode. This kind of overreaction can also happen to bats, it's just not usually in response to viruses. Instead, it seems like their unique immune system may leave them vulnerable to non-viral invaders. The most infamous example of this is white nose syndrome, a fungal pathogen which has devastated bat populations in North America. Some researchers think the bat's dampening of inflammation, especially during hibernation, makes it easy for the fungus to infect the bat. Then, once the bat awakes, its immune system does react, only it goes too far, which can lead to the bat developing a life-threatening form of systemic inflammation. So basically, the reason they die from white nose is similar to why we die from viruses like MERS and Ebola. That may mean that the key to saving bats from this fungus, and us from the deadly viruses they carry, may lie in further research on bats. And also, if we're being selfish, we have a lot of other diseases characterized by inflammation, like heart disease and diabetes. So studying their inflammation system may lead to treatments for our chronic conditions. And the same goes for studies on the ways that bats keep viruses at bay. Right now, we only have effective antiviral drugs for about 10 of the more than 200 viruses that can infect humans, and very few broad-spectrum antivirals. If we can discover more of bats' tricks, we might be able to use them to develop therapies against the diseases they host and other dangerous viruses. Plus, all this research might help us live longer. Many researchers think bats' immunological adaptations are also behind some of their other superpowers, like how they seem to rarely get cancer, or how they live incredibly long lives for animals of their size. Usually, little animals live fast and die young, but Brandt's bats can live for over 40 years, even though they only weigh 4 to 8 grams. So instead of looking at bats as species zero, we should think of them as flying keys to longevity and resilience. And in the end, they're going to be our allies in health, not our enemies.
어느 신생아의 버킷리스트. 깨끗한 물 마시기. 살균.
We've now talked about bats, birds, and even weird ballooning spiders. But there are snails that fly too. Underwater anyway. But it's still really cool and totally counts as flight, since both air and water are fluids. Hank here can explain.
Birds fly, fish swim. We learn this when we're 2. But of course, things in nature are never quite so simple. One creature that muddies the waters, so to speak, is Limacina helicina, an Arctic-dwelling species of sea butterfly, a type of mollusk. Rather than swim like most other aquatic life, this creature seems to fly through the water with tiny wings. And scientists studying these wing movements noticed something interesting. They looked remarkably similar to the wing movements of hummingbirds and fruit flies. But why would you need to fly in water? Isn't flying different than swimming for a reason? Well, the answer lies in a concept from the field of fluid dynamics called the Reynolds number. The Reynolds number is used to predict how a fluid behaves based on the speed of a movement and the physical properties of the fluid. A high Reynolds number describes fast, turbulent movements, such as humans swimming through water, while a low Reynolds number describes slow, smooth, or laminar movements like that of this sea butterfly. But what's really interesting is that the Reynolds number for these sea butterflies flying in water closely matches the Reynolds number of fruit flies flying in air. Because while water is denser and more viscous than air, sea butterflies are bigger and slower than fruit flies. So from a fluid dynamics point of view, the numbers work out about the same. This means that the water and the air behave similarly when these two creatures generate lift through their flying movements. But why fly at all? Why not just swim like most of the other self-respecting ocean dwellers? Well, like many things in nature, this unusual behavior may be motivated by the need to feed. Sea butterflies feed by deploying a large spherical mucus web that captures plankton, as you do. While feeding, this sea butterfly is neutrally buoyant. It will continue to drift in the ocean currents, neither floating nor sinking. However, if disturbed, it will retract into its shell and sink. It's no longer neutrally buoyant, so it can't just swim back to where it needs to be the way many fish would. To make its way back to where the food is, it flaps its wings to generate lift until it can redeploy its web. This is a great example of convergent evolution, when two different creatures with only distant relation to one another develop similar behaviors to adapt to similar environments. In this case, sea butterflies and fruit flies both evolved to use flight mechanisms that manipulate the fluid around them in similar ways, even if the fluids themselves are completely different. Maybe we should start calling sea butterflies sea fruit flies. Then again, maybe not.
Could we play that clip of the flying snails again? They're just so adorable. I could watch those little flappers all day. But that's it for our dive into the weird world of animal flight. Thanks for watching this SciShow compilation. If you enjoyed it and you want to keep learning about stuff that flies, check out our compilation about the coolest birds ever, or our whole playlist. And if you want to help us make even more videos, you can check out patreon.com/scishow.
Fuck.
hit the pub.
Little light friend?
Mm-hmm. That was the last one, isn't it?
Chosen Warframe suits
Oh,
you.
pineapple. Let's see.
Mine. Said there's a dump, but it's my dump.
Hmm.
I'm not just someone's daughter. I'm me. I'm Kaylee. Of all the people to name me, I never thought it would be him.
Hmm.
See you soon?
Did you come to talk about mining? How did you know that's my favorite subject? Acknowledge you? Gratitude you.
I believe he means to say thank you.
Acknowledge you? Gratitude you.
I believe he means to say thank you.
I can do great things with this. Be great. Do great things.
Have you met my wife? I wish I hadn't. Okay, forgive me. That was cheap. Pleasure transacting with you. Keep safe.
Deimos is unfolding before us like a puzzle box. I must have more samples.
Hmm.
I look forward to your return.
What did he sell?
Mm-hmm. I shall languish in weary solitude until you return.
Greetings. Your presence is always a gift to us. Perhaps we can make a trade. I trust this doesn't exercise caution whenever possible.
The boy was rash, no doubt.
gallivanting across Deimos on secret odysseys, coming back with infested on his trail. Well, he paid for it. Scolded. Shall we? Thank you, dear. Very kind.
Ah.
Go on, dear. Have a good rummage around. Let's sift through the wreckage.
Shit. Oh. Ah.
Go on, dear. Oh, magnificent. Why they bothered packing all this, I'll never know. Plenty more left if you want a second helping. Let's you and I have a chinwag. May you have much joy of it. Goodbye, dear. I'll see what else I can unearth.
I do know, what we look like. I always did. But you didn't hesitate, did you, to help us?
Hmm.
There are fascinating things down in the exocrine. Grotesque, yes, but survival isn't pretty.
Was it 9?
Until next time.
That woman, I never could persuade them to throw anything away. Always nice to see you. Do stop by again.
What should I buy? I mean,
Thinks this family may not have a future. Monotony is bearable. Hope? That'll kill you. Indeed. See you around.
only the trophies.
Don't you? The feeling of splitting open a nice, fresh ostomy. That heady smell of acetone, liver, and corrosion.
Could not have been tried. Not exactly. Those are not fish guts.
You know where to find me.
tech. Nothing. Grandmother. Mother. Nothing. Father.
I said he's gone. Put the shard away. Move on. And she cut me with it. Over and over. And I just stood there. I took it. Every slice. I had to. You understand?
Arc Bronco Prime. Not sure about that. That one could be useful. Ammo efficiency.
All satisfactory. Don't go getting infested now.
I have the honor of a name and a little taste of freedom. Whatever you're doing out there, Tenno, keep at it. Don't get lazy out there. Bye for now, you shiny thing.
I've been here a long time. I know what you need to survive this place. Remember, they'll be seeing you again, I'm sure.
Hello. Greetings. I am prepared to assist you. I trust this to be pragmatic in all aspects of life.
Cool. So my prime, Akabronka Prime. So my prime, you're saying.
Well put together, operator. Now get out there and cut down
Some
and make the Lotus proud.
Yeah. Yeah, magazine size is 200. Well, it's not like it's an Exless mod or anything. Ah, this weapon is old. Still using cars to vanishing. Status chance using Great Hider. Ah, shit. Oop. Come to think of it, I have spare slots now. Soma. Bronco. Could change appearances. Ooh, this thing is old. Really fucking old.
A fearsome appearance, Operator. You will strike terror in your enemies.
Guess I didn't put any form in it. Hmm. Does it? It's a status chance. Status per projectile 28%. Bronco. Damzavati. Not if I do this. Oh, I mean like that. Cold and viral? That's peculiar, I guess. Yeah. Maybe I should give this a shot. The critical stat. Projectile multi-shot. 15. I don't know, it's just a mod. May not be worth it. I'm gonna run a test anyway. Cephalons, Mars.
You are a true hunter. Where would the sanctuary be without you? You may explore the sanctuary.
When I have him testing. Oh, attack. Wait. And then I could... Ah, that's complicated. Ah, shit. Vital sense. Critical. Some prime. I guess it works better on... Wait, how does it? Oh yeah, it doesn't have a duration. It's kind of gimmicky. Nine. Ah. I keep forgetting their names. Not really. Dun, 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 dun. Shit. Ah, fuck. Why couldn't I use it? Scratch that, but that. Vigilante. Oh shit. Caliber. Caliber. Hmm. That's much less. Hmm. Shouldn't their stats be better? You know, there are many good mods nowadays. Huh. Hmm. Ah, that's. That's not very good. Each hit. I don't know about that. Oh, spread is enormous. How am I supposed to use this? I mean, real shotguns are like not like that, you know. Maybe, maybe if it's that short, maybe. I wouldn't like it though. Oh. I'm gonna have to remod this thing if I'm ever gonna use it. Not very useful. Yeah, come to think of it.
Operator, you have remembered well how the Tenno arm themselves.
Martyr symbiosis. Martyr. Shit. I may have to change this shit. I don't think that's necessary. Up to
Operator, are you enjoying the view?
Sure. Yeah, a lot of slots. A lot of slots. Maybe I can make them again. Yeah, Umbra Forma, motherfucker. I think it's best to just shit. Right. That's gonna take some time. Projectile speed is slow. Maybe I should put them up for that one. Yeah, that also has flight time. I should probably get that. Not sure if that's the Maduro or something. Oops.
Mission complete. Excellent work, Tenno.
Can I projectile? Shit. Ah, fuck. I wasted 2 forma.
Operator, you have remembered well how the Tenno arm themselves.
no.
Your duty in this experiment is to dispatch as many specimens as efficiently as possible. When the time comes, I will open the next data conduit.
Now come to think of it, yeah, they also play mods. Leave things. Now come to think of it, yeah, now I'm mastering rank 30, true master. So even though I use forma on my equipment, they don't decrease in capacity usually. Except for Kuva weapons and such, which can go over 30. Hmm. 40% faster isn't a lot. It's better. Manageable, I guess.
A new data conduit is open. Our experiment moves to a new zone. Hurry, Hunter! The conduit is closing fast. Hunter, the sanctuary will go on without you.
Did they all come out at me? Hmm. Is it all volatile? Volatile. No. Bounce blast radius. I don't even know where I got him. Yeah. Just exploded. Bounce? Bounce. And blast radius. Well, that's handy.
Operator? Did they anger you in some way?
What glaive did I use? Zoris is nice. Ugh. How about Orpheus? Glaive. Throne? Throne. Lily. Is that it? I keep seeing. I thought there are more.
Everything in orders, operator? Is that a pun? I will attempt to bypass this fault.
Oh, volatile rebound. Damn, Jugulus, Carnus, Sexum. I do not have this? How much is it? Rebound. 10? I mean, it's buyer sellers. On the other hand, it has a very different opinion. Oh. So I guess it's added very recently. The rebound. Is that all, by the way? Whirlwind. Different. Power. Throw. Wait. Oh, it changed. Throw damage. Oh, that's not bad. So, uh, that's not it. I guess there are. That's those that are not actually. charged throw damage. Attack range. Attack range. Is it also applied to other stuff? Ow. In terms of range, this is pretty good. Also fast. Base damage is, I guess, a lot better. Throw. Critical status. Better critical stats. Damage E. Much better damage. Heavy attack. Guess. Maybe not. Why did I put this in? Oh wait, I have to get that one first. We can buy it.
Excellent armaments, operator. Please return covered in blood. Safe and sound.
I want to buy but a rebound. Sure. Ha ha. Could be interesting. Oh shit. Shit. Shite. Hard throw. Explode on impact. Organ. Shatter.
Operator, are you enjoying the view?
I think this is more. I think this is more useful.
Your little lich is coming up in the world, Tenno.
The multitude of creatures you have immortalized would cry out in thanks.
Hmm? I guess they upgraded it. Why it becomes 2 explosions? What are the differences? Huh. Hmm. Oh, wait. Was it always color? Why does this look like a different color? Huh? Yeah, I'm using the same color. Oh, that's odd. Hmm. Do I get? I'm not sure how to feel about that. This is better. Explode and bounce. Critical damage and such. That's a lot of range. I guess also a lot of damage. Not bad, actually. I'm gonna put it in this one. Though. Zoris. Also, if it's 3 meters extra, then it could be more beneficial to other ones, but still, it could be less than this. I think this is more appropriate. And the obvious. It's been a while, hasn't it? I know about that. Oh wait. It happened once. What the fuck? While blocking? Blocking! What? Wait, in the air? Are you kidding me? Wait, I think it was in the past. What? Oh. Without fully charging it. That's the opposite, I guess. Before I had to fully charge it and time it right. Now at least they fixed that so that special function still works. Let's see, Astra Fury and volatile quick return. What does a volatile quick return do? Sure. Obvious. Is the damage good, by the way? I remember it being lower damage than Falcor. Base damage is a little bit higher than Zoris, but oh, actually, critical stats are the same. Same. So it has a little bit higher damage, but it has a much less range. Also, much less damage than Falcor. No. No, actually, not that much. Maybe they changed it. Huh. Falcor has a little bit more damage and range. Medium range, I guess. And high status, but low critical. So I think my pick is Zoris. Rapidly and with great devastation, chaining combos infinitely. Did it? So just now the heavy attack does nothing while just holding it. I guess it's a guaranteed thing. Combo crit, no, throw. Spoil the strike? No, that's not it. Da. Not combo duration, what is it? Cropped charge. Initial combo 30. 30. Maybe I should do that one. That's not very good though, for regular purpose. It's not bad. How's the combo duration? Did it? It's infinite, so still. Would not be great on regular use, though. It does a surprising amount of damage. Didn't I put... Yeah, viral. Still does... electric damage and guaranteed electric proc 2. Not bad, I guess. Status chance is 20. Critical chance is much higher. Nice. 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 Oh yeah, come to think of it, I think I wanted to make a separate loadout for a dual wielding glaive and a secondary. Then I didn't have enough loadout slots, but now I do, so maybe I'll do that now. How about with some different weapon, maybe? Bam para bara bam. Examination from Street Sweeper. Nova Kuken. Slot. Duplicate and rename. Oh, what? Didn't mean to do that one. Duh. Duh. Is this the good one? Not sure if this is a good choice. Zors. Oh well. That's how it goes. Six, maybe? Oh shit. Mm. Yeah, but do I have a Naros? Only Affinity? Huh. So I cannot use the secondary. Is that the only way? Ugh. Anyway. I'm gonna get back to training.
I claim this territory in the name of yours truly.
Data conduit is open. Go now. Hunter, you are running out of time. Enter the data conduit. Hunter, the sanctuary will go on without you.
Oh shit.
Navigation has been updated with new regions. Chaos is spreading.
Naros isn't really for killing stuff. That's not very fast at leveling, probably. Maybe I should at least try.
Your duty in this experiment is to dispatch as many specimens as efficiently as
Oh, Kiara? Alright, I didn't equip any pets just in case. So I cannot see the enemy.
A new data conduit is open. Our experiment moves to a new zone. Hurry, Hunter. The conduit is closing fast. Hunter, the sanctuary will go on without you.
I need a support. Let's make it. Theron and Bolt and Trinity.
transference still holding.
I think I should bring this to Simulacrum. I think I should bring Bubonico to Simulacrum too, to see how actually strong it is. Oh, only 100.
Data conduit is open. Go now.
Suddenly low gravity? Come to think of it, what's the blast radius of this thing? Like 7?
A new data conduit is open. Our experiment moves to a new zone.
Oh, as long as Aaron is there. That's pretty dirty. Sarah is doing the job, but not as good as I hoped.
I have opened a new data conduit. Proceed immediately.
Infested again. I guess this guy is going to zone 8. To think of it, did I put crit mods on this?
Go further. I require more efficiency. The specimens no longer interest me. It is you I study.
It's boring in my opinion. Same thing. Trainer still give more. Give more. Oh yeah. Did I make Korra though? Maybe I already had, so I already made Korra. Let me check my note. No, Korra isn't in the list. Oh well, might as well accompany to Zone 8. They're not going further.
Hunter, you are running out of time. Enter the data conduit. Hunter, the sanctuary will go on without you.
Ubanico.
Well put together, operator. Now get out there and cut down the and make the Lotus proud.
What? Wait, what? Ah, come on! I miss. Ah, shit. I misapplied form. Ah! Ah! God fucking damn it. Wow, really?
Operator, did you hear that? It said cosmic background radiation is a riot.
Maybe I should really. Hmm. Are you kidding me? Why do I even bother?
I claim this territory in the name of yours truly.
So, yeah.